Rate of change. So, rate of change, I froze the screen, let me change it. We're looking at rate of change today. So, there's different ways that you can think of rate of change. Rate of change is basically a ratio of dependent variable, which I'll talk about in a second, to independent variable. And I've done this definition different ways in the past, but that's really what it is. It's the ratio of the dependent variable to the independent variable. And some examples of rates of change would be things like miles per hour, feet per second. We think about those things in science all the time. So if you want to put a little parentheses where you have your MPH for miles per hour. Oh, miles per gallon is another good one in your vehicle. How many miles can I go with a certain amount of gas? So there's a formula for rate of change, and we're going to use the change symbol, which I've shown you guys before. It's that delta, looks like a triangle. So it's the change in y to the change in x. This is your dependent, is your y, and then x is your independent. And there's a formula that we use for this sometimes, and it has y with a little 2 minus y with a little 1. These are not powers, they're little, and they're kind of subscript, which means they're below. It means the second y minus the first y over the second x minus the first x. So this is your change in the dependent variable, and this is the change for your independent variable. So I know you guys have talked independent and dependent variables before. How do we know the difference between independent and dependent?
Dependent you can change, and independent you can't change.
It's backwards.
Okay.
So independent is the things that we can change, or that we choose, or that are given to us sometimes in problems. The dependent is what depends on what you're choosing. So let's look at an example. So this says heights. The table shows Stephanie's height at ages 9 and 12. Now, she was 10 and 11 in the middle of this, but they only recorded 9 and 12 for whatever reason. And so they're wanting us to figure out what is the change in Stephanie's height from ages 9 to 12. Okay, so her age from 9 to 12, we're looking at the changes in height. So she went from 53 to 59. What is that change? 6. So what I actually did was I subtracted those, right? So that's subtracting those. And so this would be 6, I guess it's inches, 6 inches. So we'll put that there. And it says, over what number of years did this change take place? So it's from 9 to 12. How many years is that? So that's 3 years. Okay? So this change is 6 inches, and this change is 3 years. I like putting that next to the table so you can see. Write a rate that compares the change in Stephanie's height to the change in age. Express your answer as a unit rate and explain its meaning. So sometimes if it's not an experiment, it's a little harder to do independent and dependent variables. But a lot of times time is going to be your independent variable. So from 9 to 12, this would be your independent variable, and then the height would be the dependent. And the reason is her height is going to depend on how old she is. So she really didn't get to choose her height, and she didn't get to choose her age, but time a lot of times will be your independent variable because time just happens. But the height depends on her age. Okay, so if we're looking at this and we're doing the change in the dependent over the change in independent, we would be doing 6 inches over 3 years. And you take 6 and divide by 3. And that gives us, how much? 6 divided by 3? 2. So I get 2, and then these labels help me know how to label it, inches per year. So that was sort of her average. Now, did she actually grow exactly 2 inches every year, do you think?
No.
No, but this is an average rate of change or an overall rate of change from 9 to 12. We didn't worry so much about what happened in between, but on average she grew 2 inches per year. A lot of things in real life aren't going to be in a perfect pattern, but you can come up with something close. Okay, so that's our first example.
Are you the restroom?
Yes. And the next part, don't forget to sign out. Fundraising. The table shows the amount of money a booster club made washing cars for a fundraiser. Use the information to find the rate of change in dollars per hour. Now this is a really big clue, because dollars per car could be written dollars per car like this. And so that tells me how I'm going to set up my final thing. So that's a clue. All right, so if I'm looking at it, here's the number of cars they washed, and here's the money that they're making. And there's a lot of data points. It's more than 2. So what I need to do is just pick a couple. And you could pick any 2 data points you want, but you need to have the number and the money that go together. So I could pick 5 and 40 and 10 and 80 just to be my X's and Y's. So this over here, this change from 40 to 80 is 40. It went up 40. And from 5 to 10 went up 5. So I'm going up $40 for every 5 cars. So if I'm doing my rate of change, I've got $40 for 5 cars. And they want us to take that down to a unit rate, which just means they want us to reduce. So 40 divided by 5 is 8. Good job. Sorry, I didn't see it quite fast enough. All right, so we're going to have $8 per car. And I'm going to do that because it says to do it in dollars per car and the answer. So that's how I know I set this up right. There was that little clue. Now, I could use any points that I wanted to out of this, and when you reduce, you're going to get the same answer. So just for argument's sake, let's say that I picked these 2 down here. 160 minus 20 is also 40. 20 minus 15 is also 5, so I could have got the same answers. I could have taken 160 minus 40, which is 120, and 20 minus 5, which is 15, and divided it, I still would have got $8 per car. So any 2 points, you can pick anything on that table to use because it's going to be a straight line and it won't matter. Okay, so let's go down here to driving. And these are some of the ones we were talking about that you've probably seen in science before, where they have distance on this side and time on this side. So it says the graph represents the distance traveled while driving on a highway. Use the graph to find the rate of change in miles per hour. Ooh, they're giving us a clue in miles per hour. That tells me I need to have miles divided by hours. And so that makes this easy. I'm going to know how to set it up. But the information is on a graph. So I'm going to have to pull a couple of pieces of information off the graph. So if I have 160, that means I went over 1 hour and up to 60 miles. So I could kind of make my own little table if I wanted to. So I can have time, and I can have distance, and I can put these in there. So I've got 1 hour for 60 miles. I also have 2 hours for 120 miles and 3 hours for 180 miles. And if you want to organize it in a table just so they kind of all look the same, you can. And then I'll talk about the picture a little bit. So I only need 2 points from this line to figure out what the change is. So it says I'm going to do miles per hour. So miles is my distance. So I'm going to take, I went from 60 to 120. So that's an increase of 60. And I'm going from 1 hour to 2 hours, so that's going up 1. So that means I'm going to have 60 miles for 1 hour, which is just 60 miles per hour. I wrote 6 instead of 60, hang on. And so you can use any 2 points from that graph that you want. You can set it up in a table if that makes you feel comfortable. But I'm going to start talking about the graph a little bit because the graph's going to be a big deal. You can also get information straight out of the graph, and it's really faint. There's these little dashed lines. If I look at going from one point to another, from here to here, I can see I went from 60 to 120. That's going up 60. And I'm going over 2 boxes from 1 to 2, but that's 1 hour. And then if I come up and do a different interval from here to here, I'm still going to see going up 60 and over 1, 60 miles in an hour, 60 miles in an hour. And I could keep doing that. I could also do something crazy, which I'll show you. If I go all the way from this point down here at the origin up to that top point, let's say, I could make a really big triangle like this. And I would be going up 180 and over 3. So 180 divided by 3 is still 60 miles per hour. You can make any triangle that you want if you're using the points that are on the graph and showing how it's going up, either a little bit at a time or a lot at a time. And because it's a straight line, you're always going to get the same rate of change, regardless of what you do. We're going to call this slope in the next lesson. They call this slope. Basically, it's how steep the line is. Okay, so let's go do another one, and we'll try to use the graph on this one. So it says, use the graph to find the rate of change in miles per hour while driving in the city. I'm going to give you another way to do rate of change. Sometimes, especially when we're talking about other problems, they're going to call this the rise over run. And if you're dealing with a graph and you don't want to make a table and you're not really wanting to write out a big formula, this is a great way to look at it. So if I go over to my graph and go, okay, from this point to this point, how much did I rise? So I'll do that in orange. So it looks like I went from 30 to 60. I can tell by the points they give me, and it's in the middle. From 30 to 60. How far is that? From 30 to 60? 30. So my rise is 30. And then I'll do the next one in yellow. I want to do the run. The run is like the horizontal piece. So I went up 30, and then I went over, and I have to use my labels from 1 to 2, and so that's 1. So this is 30 miles, and this is 1 hour if I'm using the labels. So 30 miles in 1 hour. And basically, I just got the answer just by looking at the rise and the run. And so I get 30 miles per hour, which is what it said. It wants the answer in miles per hour. But when they graph, here's a little tip. Your y-axis is always the dependent variable, and your x-axis is always the independent variable. And I'm sure you guys talked about that a little bit in science too, but that's always the way that it's set up. You shouldn't set it up any other way. Okay, we've got one more. I know this is super exciting. Physical science. So here they're giving us an application that's science. The table below shows the relationship between the number of seconds y it takes to hear thunder after a lightning strike and the distance x you are from the lightning. So sound takes a little bit to travel, so there's always a little bit of a lag between when you see the lightning and you hear the thunder. This is just giving us distance and how long it takes for you to hear it. So, and they didn't give us labels. I'm not really for sure what these labels are supposed to be. They've got seconds. Let's say that... Right, I'm just trying to figure out what the distance is measured in, kilometers or miles. Let's just say it's miles. I'm not sure that's accurate, but they didn't have that in the problem, and so we're going to add that in just to have a label. So yes, the distance on this is actually going to be independent, because how far away it is just how it happens. But the time it takes you to hear it depends on how far away it is. So this is one of those rare situations where we're going to put time on the y-axis. So I've already set up a graph for us to save some time. And so down here we're going to have miles, so we'll label that. You always have to label your graphs. And over here I'm going to have seconds, and that's my time. And it says to graph the data, find the slope. Slope is another word for rate of change. And then we'll explain what it means. So it starts off at 0, 0. Then I have 1, 5. Now notice how this is numbered 2, 4, 6, 8. So how do I put in 5?
Right in the middle.
Between which numbers?
4 and 6.
4 and 6. Good. Right in the middle between 4 and 6. Excellent. And then 210 is right here. And then 315 is here. Got a visitor.
We do. Sorry for interrupting.
That's okay.
Just real quick, I introduced you all to Mr. David. This is Mr. Jacob. He's the assistant superintendent on the build project, so we're going to see a lot of him around as well. And I just want you all to know he's a friendly face. We're good. And do you see what he's wearing? Just like we promised, that's what they'll be wearing out there. So when you see him, a lot more activity this week out there. I just want you all to be safe and mindful. Good morning. Thank you for making it. I'm happy you're here. So just be mindful, we have a lot of activity out there. We put signs by the doors to remind you not to go out the senior lock area and or that main door over here. Because it's, in fact, I think your grandpa's going to be taking a tree down this morning. So, you know, I don't want you guys out there. I like you way too much to go out there and get hurt. So. All right, questions for Mr. Jacob? Anything? No, you guys got it? We know the drill now? Okay, right on. Thank you.
Nice to meet you.
Thank you.
Oh, I'm sorry, that's Miss Billabore.
Hey, that's okay. He won't remember anyway. There's too many faces. All right, so we're just graphing these points. We're right at the tail end of a lesson, so just kind of watch, and I'll make you a copy. Okay? All right, so we're just graphing these points. You guys might already have this done. 420 and 525. So if this is a rate of change that's always the same, it should make a straight line. So if we connect these, it makes a straight line. And you could have thunder farther away, lightning further away. So I'll just put a little arrow on the end there. And then it says to find the slope. Slope's just another word for rate of change. We're going to get into that a little bit more tomorrow. And so we're going to use our rise over run. So we can pick 2 points. Let's pick points that are on whole numbers. So let's...
0, 0.
0, 0 is an excellent number to use. So we're going to use 0, 0, and let's use 210, just because I think that's easy. So my rise, if I go from 0, 0 to 210, would be 10. And my run over here is 2 seconds. And so I would have 10 seconds, 2 miles, for every 2 miles. And if I divide that, I'm going to get 5 seconds per mile. So basically, if you're going to hear the thunder 5 seconds after the lightning happens for every mile away that it is.